Okay, so good evening. I'm Calvin Joseph, and today I conduct your week 9 problem solving and doubt clearing session for the course Control and Tuning Methods in Switchman Power Converters. So today we'll be discussing about these topics. That is, what are the dynamics of linear time invariant systems? What are the eigenvalues? What is the interpretation of an eigenvector? Then we'll consider what is known as a phase portrait, and we'll also solve certain questions. Okay. So this session was preponed because during the week after the next week, we would not be in campus, so it would be difficult for us to conduct. So we are preponing the sessions so that before the assignments, these sessions have already been recorded and already been those stuff has been taught. Okay. So let's start. So this is week 9. Okay. And we will consider a dynamical system. So your boost converter LTI system, your boost converter.
No, it is non-linear.
Okay. So your boost converter is non-linear. And okay, so but we write the boost converter state space, right? We write it as x dot is equal to ax plus b into vn, where x is your states. Okay, x is a vector which has your states il and bc, right? So we are writing these equations for the boost converter. Then why is it non-linear?
It is piecewise linear. During on state, we can write uh, one set of equations, and
Yeah.
during off state,
So basically, when the switch is on, the A B values will be different, and
Yeah.
it will be different for when it is on. So
Yes,
that's why
correct.
it is non-linear.
Yeah. So when q is 1, we have our x dot is equal to some a1x plus b1bn. This is how this is the equation governing the dynamics of the boost converter in this mode. Q is equal to 1. Then when q is equal to 0, we get a x dot is equal to some a0x plus b0vn, right? So this a1 is not equal to a0, your b1 is not equal to b0. There may be cases where they're equal, like in a buck converter, a1 is equal to a0. In a boost converter, b1 is equal to b0. So this is possible. But at least one thing will be different. Okay, so they are linear in their mode, but when you combine it and you switch it as a system, it is non-linear. Okay, so now we have let us consider this x dot is equal to ax. If you look at this, uh, this, it is like a first order differential equations. It is a set of first order differential equations. So let us consider a simple case. Suppose we have some x dot is equal to some ax, where x belongs to R1. That means x is a scalar. So x is a scalar. So how will this differential equation, what will be the solution for this differential equation? Any idea how it will look?
sir, can you repeat the question?
Okay. So x dot is equal to capital AX, this equation, right? In this equation, your x is a vector n cross 1. That is, you will have your x is equal to some x1, x2, x3, etc. What I did was, I'm going for the simplest one. So I have one x dot is equal to a into x, or small a. So your okay, I think it's a bit more mathematical. Let us say first, let me say this x dot is equal to ax, capital AX. Okay. So this actually is some x1 dot, x2 dot, x3 dot, right? Some a11, a12, a13, a21, a22, a23, a31, a32, a33, x1, x2, x3. Okay, this is your x dot is equal to ax. So this is your x dot, this is your a, and this is your x. Okay, so x is a vector. So if you will see it, so this is 3 cross 1. Capital A is 3 cross 3, and x dot again is 3 cross 1. Any doubts in this part? In the representation, mathematical representation of this?
No, sir.
No, sir.
Okay. Now what I'm doing is to make it very easy. I'm just considering 1. That is, I have my x1 dot is equal to a11 x1. Okay. I am just considering a simple equation. So this is for the case where x dot is equal to a x. So this is a first order scenario, and this order which we have considered is a third order. Like not like we have 3 states. So now I'm just considering a one state. X1 dot is equal to a11 x1. Okay. So what will be the solution of this? Any idea?
E raised to a11 t into x0, x of 0.
Okay. So as you're saying, x1 of t is equal to e raised to a11 t x1 at 0. Right?
Yes, sir.
Only this part.
Ah, yes. Only we are considering only this. Like I am. This is case A where there are 3 equations. Now there is case B where there is only one equation. Where we are just focusing on case B where there is only one equation. So we have x1 dot is equal to a11 x1. That solution, as you have told, x1 of t is equal to e raised to a11 t into x1 of 0. Okay. So now, how will we say whether this is stable or unstable? What should be the criteria?
If a11 is positive, then it is a growing exponential, so it will go unstable.
Okay, so,
If a11
that's it.
if a1 is negative, then it is a decaying exponential. As time increases, it will go to 0.
Okay. So if a11 is greater than 0, it is unstable. If a11 is less than 0, it is stable. Right? Okay.
Yes, sir.
So now, let us consider the case where we go for a second order scenario. So, like in the converters which have been taught, like a buck converter and boost converter, right? What we do is we consider the state. This is known as a state vector X. It consists of state, inductor current IL, and the voltage across your capacitor. Okay. It could be a buck, it could be a boost, but we have 2 state, IL and BC. Okay. Let me just draw a boost converter simple. So this is your input voltage over here. You have your inductor over here. You have your switch over here, Q. You have your complementary synchronous switch here, Q bar. You have your C over here. You have your R, load. So the voltage across this capacitor, that is VC, and the current through the inductor IL, they are considered to be the states. So why do we usually select IL and VC as the state is because they are continuous, right? Your inductor current cannot change instantaneously because the property of an inductor is that the current cannot change instantaneously. For a capacitor, what is the property? That you cannot change the voltage instantaneously. So these states, IL and VC, since they are continuous, that is, they don't have any abrupt changes, that's why we use the states IL and VC. Okay, so that is one point. So we represent IL, VC, etc. in terms of X. It is a vector, right? X is a vector consisting of IL and VC. So now we can get my X dot that is equal to some AX plus B into Vn. Okay, so my X dot is equal to AX plus B into Vn, right? And as I told, when Q is equal to 1, you have one case. When Q equal to 0, you have another case, which you already have told. So the stability is governed by the matrix A. It depends on what are the eigenvalues, etc. of the matrix A. So we will consider a simple case where we consider what is known as an autonomous system. Autonomous system means what? Your input U is 0. So your equation becomes equal to X dot is equal to A into X. So this is an autonomous system, example of an autonomous system. Since buck converter, boost converter all are second order, we will consider the second order case. Okay, so we'll have some x1 dot, x2 dot that is equal to a11, a12, a21, a22 into x1 into x2. Okay, it is given in this form. So this is your matrix A. Each matrix has something known as its eigenvalue and eigenvector. So how do you find the eigenvalue of such a matrix?
By solving the characteristic equation, determinant of A minus lambda I equal to 0.
Okay. So you are saying A minus lambda I and its determinant, right?
Yes, sir, equal to 0.
This should be equal to 0. Okay. So when we find it, how many eigenvalues will we get? 2. Okay, correct. We will get 2 eigenvalues. Okay. What could be the nature of the eigenvalues? That it could be real, it could be imaginary, it could be positive, it could be negative. What do you think would be the nature of the eigenvalues? What are the possible scenarios? What are possible cases?
It can be
They
anything,
can be
sir. Real,
real and
imaginary, positive, negative, anything.
Correct, correct. Yes. Yes. So you are saying you're correct. So we'll consider cases. So then we'll have uh, so there are two eigenvalues as you have told, lambda 1, lambda 2. So one case is lambda 1 is positive, lambda 2 is also positive. One case is lambda 1 is positive, lambda 2 is negative. Another case is lambda 1 is negative, lambda 2 is positive. It doesn't matter because it depends. We will say which is lambda 1, which is lambda 2. It doesn't make much of a difference. So these are actually just one case. Another case we can have is lambda 1 is negative, lambda 2 is negative. This is one case. Next case we will. So these are the cases when all your eigenvalues are real. They are real. Now we will have another case where your eigenvalue will have a positive real part. Okay, let us say as plus alpha plus minus j beta. It could be this or it could be minus alpha plus minus j beta. Because if it is imaginary, it should always come in pairs. They should be complex conjugates, such that their product would be real. Okay. So these are some things which you have known. So we have typically 1, 2, 3, 4, 5. So we have 5 different types of eigenvalues which you get. 5 different types of combination of eigenvalues you can get for one matrix. Okay, and we are still at the simple second order matrix. Okay, and we will limit our discussion to second order only. So now you tell me in which case your system will be stable, in which case your system will be unstable.
If the eigenvalues are real, then both should be negative. If they are complex, then the real part should be negative.
Okay. What about others? Anyone has any other? Do you agree with it, or you have any other contradictory thing? What do you think? Okay, so what he told is correct. Just we have to, I'll let you know, lambda should be negative. Your lambda should be negative, and real part also should be negative. So I'll just tell one. Okay. So your lambda, both lambda should be negative. And it would be easier if I would write your solution. That is, let us say you're basically interested in solving this differential equation. So when you solve a differential equation, you would need what you say, you would need the coefficients of the differential equation that you have. You would also need to know the initial condition, or initial condition could be something. Okay. So now when you will solve these two differential equations, what you will get is some x1 of t and some x2 of t, right? You will get something. So those will depend on your eigenvalues. They are dependent on your eigenvalues. So there was some. So this is kind of like your auxiliary equation which you guys used to solve, right? If you remember for differential equations. Okay. So now, and these eigenvalues are your roots of the auxiliary equation which you used to solve. So it will be something like some, what variable I can use? It could be some m1 e raised to lambda 1t plus some m2 e raised to lambda 2t. This would be some m3 e raised to lambda 1t plus m4 e raised to lambda 4t. Okay. If you will see these equations, you will understand why your lambda should be negative. If your lambda is positive, then these will increase. They will rise exponentially. So it will become unstable. Your lambda has to be negative. Your lambda should be negative. But what happens if one is positive and other is negative? Will it be stable or will it be unstable?
Unstable, sir.
Unstable, correct. Because one might decay to zero, but the other increase and rise a lot, right? Or it will go to infinity. So it is unstable. Okay. So based on that, these have been categorized into 5 different types of nodes, 5 different types of positions, or 5 different variables we call it. I think I'm not getting the correct term. I'll let you know. So lambda 1, lambda 2, both are positive. It is known as a stable node. It is known as a, no, sorry. Both are positive, it is unstable. Both are positive, it is known as an unstable node. If one is positive and one is negative, it is known as a saddle point. If both are negative, it is known as a stable node. If they are complex conjugates and there's a positive real part, it is known as an unstable focus. And if it has a negative real part, it is known as a stable focus. Okay. So this terminology, it would be good if you remember. So I've written in this expression, it's not very neat, everything, but you could also make notes and you could remember this. That is, depending on the sign of your eigenvalue, you can say whether that equilibrium point is stable or unstable. So if both are positive, it is unstable node. One is positive, other is negative, it is known as a saddle point. Both are negative, it is a stable node. If one is if the real part is positive in a complex conjugate pair, it becomes unstable focus. And if the real part is negative in a complex conjugate pair, it becomes a stable focus. Okay. All right. So now Arun has told how do you find the eigenvalues. What about finding the eigenvector? What do you do for that? Okay, how many eigenvectors should be there?
Two, sir.
So there should be two eigenvalues. We will have two eigenvectors as well, right? So we have sums. How do we
Yes.
find value, eigenvector, etc.? Okay. So what is the formula for finding out the eigenvector?
AV equal to lambda V by solving that.
So we have some A, V bar, that is your vector, is equal to some lambda V bar, right? This is the equation. When you solve it, you will get your eigenvector. Okay. So, any doubts in this point? So we will also be solving sums, so to become more clearer in that, right?
Sir, if there's an eigenvalue that is exactly repeating, like for example, lambda equals to 1 comma 1, is there any significance to that? Like some special system or something? Or like if the values are exactly identical?
The values are exactly identical. One issue is there is, uh, I don't exactly recall, but there's something known as multiplicity of the eigenvector and all that. There are some, it's a special case actually. It is a special case. So, how do you tackle that? I don't remember, but there is a special case. Both the eigenvalues are same. Like, if you have, like both your eigenvalues are getting it at 1, then there might be a case that you will have only one eigenvector. So they have to make up something known as some special eigenvector or something augmented vector or something is there. I don't recall, but there is something like that. So those are things you will learn in linear algebra. I don't think you will find that special case over here.
I think I did find one such case in this assignment problem only one. But
Huh?
yeah, anyways, the
Oh,
next week after I'll discuss it with you maybe
okay,
because
okay, sure.
now it is in the current week only. So yeah.
Okay. It shouldn't be there. It shouldn't be there. Because that has not been taught. It shouldn't be there.
Yeah, then either I'm making a mistake or yeah. Okay,
Okay. Yes.
confirm
Maybe
that next
maybe
week.
the eigenvalues might be the same, but I don't think you have to get the eigenvector in that case.
No, just the eigenvalue they asked to calculate.
Then it's
Like
fine.
it's
Then it's
basically a
fine.
match the following. Yeah.
Yeah.
So yeah.
Then it's fine. Okay, so Joshi, you're saying AB is lambda V, then V vector cancels and how to find eigenvector V. Okay, Joshi, we will do one sum. So there you will understand how do we calculate the eigenvalue, eigenvector. We will do that sum. Huh? So, acha. I think we'll start with the sums. Sums is better. Sums is best. So, let us start with this. Question 1. we have to find the eigenvalues for these matrices M and N. Okay, suppose M is given by this, N is given by this, so we have to find their eigenvalues. Okay, so let us start. We'll start question 1. We have a matrix M which is given by 2, 3, 0, 1. So 2, 3, 0 and minus 1. Okay, minus 1. Okay, so what are its eigenvalues? Let me ask Parvati. So what are its eigenvalues? What about others? What are the eigenvalues for this?
-1, 2.
Correct. Okay. It is -1, 2. Let
Yes,
us
sir. Minus.
minus. Okay.
Minus. I got plus.
We got, okay. Joshi also got -1, 2. So you all have got lambdas -1, 2. And how do you do it is, it's very easy for this case is because it is a upper diagonal matrix. So in the case when it is either upper diagonal or lower diagonal, or it is a diagonal matrix, then your eigenvalues are the diagonal elements. That is, this will be your eigenvalue, this will be your eigenvalue. Just seeing the matrix, you can tell. You don't need to calculate. For such a case, such a special case. Okay. So now we have found our lambda has -1, 2. So let us consider case lambda 1 is equal to -1. We want to find the eigenvector corresponding to this. So what do? We take lambda 1, like what formula Arun has told. He has told A into V1 bar is equal to lambda into V1 bar, right? So, let us go here. Okay. So A into V1 bar is lambda into V1 bar. So we are over here doing M into V1 bar is equal to lambda into V1 bar. So what do we have M to be? 2, 3, 0, -1. So 2, 3, 0, -1. And V1 bar, we will represent it as V11, V12. Okay. So that is equal to V11, V12. And this is your lambda 1. Your lambda 1 comes out to be -1. So this is V11 and V12. Right? So now, what do? You can write this as 2V11 plus 3V12 is equal to minus V11. And the second equation you get minus V12 is equal to minus V12. So this is fine. Minus V12 is equal to minus V12. Now we get 3 into V11 plus 3 into V12 is equal to 0. So we get V11 plus V12 is equal to 0. So we get V11 is equal to minus V12. Alright. So now your V1 bar, it is actually V11 and V12, right? So V1 bar is actually your minus V12, V12. So your V1 bar is actually equal to minus 1, 1 into some factor V12, right? This is not the bar. some v1, 2. So what do we say is that your eigenvector, we just take it as minus 1, 1. You could also write it as minus 2, 2. You could also write it as minus 3, 3. It all is the same. We usually take it in terms of 1. So it is minus 1, 1. So this is your eigenvector. Your eigenvector will point in one direction. Okay, so this is your eigenvector. V1 bar is minus 1, 1. Any doubts in this part? Or you want me to repeat it also? I can repeat it.
No, sir, it's clear.
Okay. Okay. So this is the equation for us to compute the eigenvector. So this 2, 3, 0, minus 1, V1, 1, V1, 2. That is equal to lambda 1, V1 bar. Our lambda 1 is minus 1. And your V1 bar are represented into two elements. They are two elements of that vector. So they are known as V11, V12. So I've written it over here. Now, this is for the first set of equations. And this is for the second set of equations. So the second set of equation is not giving me any useful information. It is coming equal means I'm correct. But further, I cannot infer anything from it. Okay, so this is second equation is limited. Give me limited information. In the first equation, when I do my mathematical manipulation, I am getting this what do you say, not equality, this relation. That is V11 is equal to minus V12, right? That means if V11 is 3, that means V12 should be minus 3. Something like that. So there is a kind of relation. So what V1 bar, we already defined it as V11, V12. Now, since there's a common relation, we write that relation over here, right? And then we take out the common factor V12 out. So V1 bar is minus 1, 1, V12. So your eigenvector, you could represent it as minus 1, 1. You could also represent it as 1 minus 1 also, it is fine. It is just a scaling factor. It is just a scaling factor. Okay. So it could be 1 minus 1, minus 1, 1, or minus 3, 3. Okay. So this is one method to find the eigenvector. Now let us do, now we have found lambda has eigenvalues of minus 1, 2. Let us consider case when your eigenvalue is 2. So we have lambda 2 is equal to 2. Okay, it's a coincidence, it has happened like that. So now, what method I prefer? Like this is the method I prefer to find the eigenvector. I'll use this method. You can decide which one you prefer. So the eigenvector, that is, as we have, as Aruna has told, you have mv2 bar is equal to lambda 2 v2 bar, right? This can also be represented as mv2 bar is equal to lambda 2 I v2 bar. We can also write it as lambda 2 I minus m v2 bar is equal to 0. This is what usually I use. Because when we are finding the eigenvalues, we already do this lambda I minus m. So already I have this form. Okay, because preferably you want to do things fast. So you will do this lambda I minus m. You will get that matrix. Then you will do the determinant lambda I minus m equal to 0. Then you will get the eigenvalues. So already you will have this form written. Lambda I minus m, you will have this form written. Then when you want to find the eigenvector, you will substitute. So in this case, I'm substituting lambda 2I minus m into v2 bar is equal to 0. Okay. So instead of lambda, I will just substitute the value of lambda 2. So that means what I will write here, it would be 2 into I minus m into v2 bar is equal to 0. Now this V2 bar eigenvector, I will represent it in terms of V21, V22. Because it has two elements, and I'm keeping these elements distinct from the one which we have previously used. So I'm using this way. I am giving it the numbering. Okay. So now this is 2I is what? 2002. What is M? M is 230 minus 1. So that is 230 minus 1. The whole bracket into V21, V22 equal to 0, 0. So this 0 is not a scalar. This is a 2 cross 1, 0. Okay, so this is 0, 0. So now this will come in the form 2 minus 2 is 0, 0 minus 3 is minus 3. This is 0. 2 minus or minus 1 is 3. So this comes out V21, V22 is equal to 0, 0. Right? Any doubts still here?
No, sir.
Okay.
Clear.
So when we solve this, we will get minus 3 V21 is equal to 0 and 3 V22 is also equal to 0. Seems to be some mistake over here. Why is this happening like this? Mhm. Because if I do this, I will get my V21 is equal to 0 and V22 is equal to 0. But this is not the eigenvector. Mm, right? Mhm. Anyone is able to see any mistake or anything?
Sir, 0, 0, why it cannot be an eigenvector? It will also satisfy that AV equal to lambda V.
It will, let me check. Let's check. So we have your 2, 2, 3, 0 minus 1, V21, V22 is equal to 2 into V21, V22, right? So that would mean 2 V21 plus 3 V22 is equal to 2 V21. And we'll have minus V22 is equal to 2 V22. This is not correct, no?
I am not completely sure, but I remember something studied in math.
Okay. So if you see these equations also, uh, like if we see these equations, this minus V22 is cannot be equal to 2 V22. Like it does not give any conclusion. You know, we have made any mistake.
Sir, from this also we get V22 equal to 0 and V21 equal to 0.
No, okay, even if we get from here that V22 should be equal to 0, then we get 2 V21 is equal to 2 V21. So this could be that V21 can be any value. V21 can be 0 also, or it could be 1 also, or it could be 2 also. Any value it could be. That is my confusion. Very confusing thing. Okay, let us do in MATLAB. Let's make it second. Okay, so this is our question point. What is our M matrix? M matrix is 2, 3, 0 minus 1, right? So it is 2, 3, 0 minus 1. Okay. We run it. This by N. Now let us find the eigenvalue then. It comes out to -1. Now we have to find the eigenvector. So what we find vectors must be throughout the documentation where share. B comma D. So it says B comma D. Let me run this. Okay, so our eigenvector B is 1, 0. 1 is 1, 0, that is for P. And for eigenvector, eigenvalue -1, it is minus 0.707, 0.707. Okay. So this one we got. We got it at wrote it as -1, 1. If you normalize it, you will get it in terms of minus 0.7071, 0.7071. And here we are getting B is equal to 1, 1, 0. So that we are getting over here as well, because here what did we get? We got our B22 is equal to 0, but our B21 can be any value, some value x. Since they are considering a normalized case, they are taking B2 bar is equal to 1 and 0. While in the previous case, B1 bar, we took it as, it could be -1, 1 or 1 minus 1. They, what they did, they divided it by √2. 1 by √2 minus 1 by √2. That is why they got it as 0.7071 minus 0.7071. Okay. Any questions, or you want me to repeat it? Or any doubts? So much of silence is very uncomfortable.
Sir, that
No,
division
sir,
by
it's-
root 2, is it because division by root 2, is it because that root of -1 square plus 1 square,
Yes,
that
yes, yes,
magnitude
yes,
equal to?
yes, yes, yes. Exactly, exactly. So what you got is you got your V1 bar is equal to -1, 1. They want to write it in normalized form. So they write it as -1, 1, and you into some factor, into some 1 by factor. That factor is your magnitude of V1 bar previously. So that is equal to square root of -1 square plus 1 square. So the square root of 2. That is why your V1 normalized, which MATLAB will generally show you, is -1 by √2, 1 upon rho. Okay. And
Okay, sir.
to further, and to this also, if you will see this equation, what it is saying that, acha, this equation is saying it is either minus 3v22 is equal to 0 or 3v22 is equal to 0. So it's the same. This is 0 into v21 minus 3 into v22. So minus 3 into v22 is 0 means v22 is 0. Second equation also still in 3 into v22 is 0. That is v22 is equal to 0. But your v21 can be any value x. So that is why in the normalized case they take it as 1 and 0. Okay, so this also was correct. This method also is correct. Okay, we'll do the next sum. So you'll get more confidence in doing this. We'll do the next part of the sum. We have one more sum. We have one more matrix. We have to find the eigenvalues. So we'll have this is the matrix. N is 5, 4, 6, 1. Okay. So we have N is 5, 4, 6, 1. So I want you to find its eigenvalues. Okay. So Joshi, Parvati, you also can let me know what are its eigenvalues. Okay. So Joshi is getting 3 plus 5.29 and 3 minus 5.29. Okay. So Joshi is getting 8.29 and is getting minus 2.81. What about Parvati?
I got imaginary.
Tension is he? Why? Okay. Let us check using MATLAB. Let us just check it. This is not a very good habit to just dump all the work on MATLAB, but since you guys will be giving the exam, you have to be accurate in your calculations. Okay, this is n is 5461. Eigenvalue of n. Okay. Yes, it is 8.2915 minus 2.2915. Parvati, I think we'll have to check your calculations.
Yes,
Usually
sir,
guys are always
got it.
right, but this time we have to differ. This thing. MATLAB is saying it is 8.29 minus 2.9. You also got it, right? You know, 8.29 and minus 2.29. So minus 2.29. Okay. So you got these two eigenvalues. So now both are real. So what kind of point is it? Is it stable, unstable? What is it?
Unstable, sir.
Unstable. Correct? And which type? We had 5 different types. And what was it called?
This will be the saddle point.
Saddle
One
point.
positive, one negative. Yeah.
Correct. So it is a saddle point. Okay, so it's a saddle point. So very good. You guys are paying attention. So you got lambda 1, lambda 2. So let us try to find the eigenvector. Let us try for a case. Actually, since I've just given some arbitrary numbers, that's why you got eigenvalue which has this fractional part. Usually such things are not given in the exam. So we have lambda 1 I minus n into v1 bar is equal to 0. That is 8.29 008.29 minus of 5461 into v11 and v12 is equal to 0, 0. Okay. We go to next page. So what is 8.29 minus 5? It will be 3.29. This is minus 4, minus 6, and this is 7.29. Okay, this is v11, v12. This is equal to 0, 0. So we get 3.29 v11 minus 4 v12 is equal to 0, or minus 6 v11 plus 7.29 v12 is equal to 0. Okay. So how do you solve this? Let's try one thing. Let us just add. We just add them. Okay. So 3.29 minus 6. That should be 2 minus 2 minus 2.71 v11. 7.29 minus 4, that is equal to a minus 3.7 minus 4. This will be minus 3.71. No, this would be minus 3.29.
3.29, positive 3.29.
Plus, right. Okay. So this is we got. So then we get a relation, that is your v11 is equal to 3.29 v12 divided by 2.71. That means if v12 is equal to 1, then v11 is equal to 3.29 upon 2.71, and our v1 bar would be 3.29 divided by 2.71 and 1. So can anyone tell me what is 3.29 divided by 2.71?
1.21.
So this is 1.21 and 1. So can you tell me what is the magnitude of this? That is square root of 1.21 square plus 1 square.
1.569.
Square root of that? It is the square root of this, right? Square root of
Yes, sir.
121 square plus
1.569.
Okay. So can you tell me what is V1 normalized? That is 1.21 divided by 1.569 and 1 divided by 1.569.
0.771.
Okay. And 0.6,
0.637.
0.637. Okay. So let us verify. You have done the maths. In the assignment or in the exam, you will have some option. But here, I have not given any option. So let us check it in MATLAB. So let me do this. I'll comment out because I'm not using this. Now let me do b comma b is equal to okay, did you get this 0.7722 0.6354? That's what we got, right? We got 0.771 almost and 0.637. So here you got 0.772 and 0.6354. Okay. So it's almost same. And our eigenvector is 8.2915. So we just took eigenvectors 8.29. We did not have this 15. We did not go exact. So that is why there's some numerical error. And in your exam, you have some amount of tolerance in your numeric answer. They specifically want your numeric answer. So any doubts in this? Or can I proceed? Okay, what is V and D? Okay. So your V is the eigenvector. And your D is a diagonal matrix which has the eigenvalues. So that means this 0.82915, this is one of your eigenvalue. And this minus 2.2915 is one of your eigenvalues. And that you had calculated, right? Now, corresponding to this eigenvalue, this is your eigenvector. And corresponding to this eigenvalue, this is your eigenvector. And these are your normalized eigenvector. Okay? Okay. So now we go to the next question. Let us proceed to the next question. Okay. So what are the possible types of equilibrium points we had seen? We had stable node, unstable node, stable focus, unstable focus, and saddle point. So that was what this question was about. Okay. This is question 2 also we have seen. Let's go to question 3. Okay. So now we want to convert a coupled system into a decoupled system. All right. So let us see question 3. So question 2 we have done. There are 5 types of equilibrium points. Which we had seen earlier. Now let us check question 3. We have a matrix which is given by -1, -3, 0, 2. -1, -3, 0, 2. Okay. If you will see this, you have what is your x1 dot, x2 dot is equal to -1, 0, -3, 2 into x1 into x2. Right? So your x1 dot is equal to minus x1. This is good. But your x2 dot is equal to -3x1 plus 2x2. Due to this term, that is why their x1 and x2 are coupled. Right? Some factor of x1 has impact on x2. So that's why this is a coupled system. So what we can do is we can transform this coupled system into its into a decoupled system. There is a method. Okay, we will see that method. I think Arun, you will know this, right? You had done it in that state space course.
Sir, P inverse A, P, some similarity transformation we do.
Yes. Parvati, you are saying something?
Sir, in the question it is -2, I think. So.
Okay, let me check. -1, -3. Okay, -2. Okay, good. Paying attention. Okay, and -2. So yes, as Arun told, there's something known as similarity transformation. So what do we have? We have x dot is equal to ax plus bu, and we have y equal to cx plus du. Okay. Now we want to transform it using some. We will transform. We represent instead of the state x, we will use a set of state z. So your z is some z1, z2. Okay. Assume we are doing z equal to mx, right? So what we can write? We can write x is equal to m inverse of z. Z equal to mx means x equal to m inverse of z. So what should we do then? We will, wherever x is there, we will substitute with m inverse z. So what do we get? We get our m inverse z dot is equal to a into m inverse z plus b into u, right? And then here we get y equal to c into m inverse z plus b u. So we get z dot is equal to m a m inverse z plus m b u, and y is equal to c m inverse z plus d into u. So this is known as a transformed system. Okay, this is a transformed system where your z dot is now your, this has some other a. It has some a1z, or let us say a decoupled z plus b decoupled u, and y is equal to some c decoupled z plus d decoupled u. So what is the relation which we have? We have AD is equal to m into a m inverse, BD is equal to MB, CD is equal to CM inverse, and DD is same as D. D doesn't get changed. It remains the same. Okay. So this is known as something known as similarity transformation. Similarity transformation. Okay. So actually I've done a, it should not be decoupled. Like AD can be anything. Can be some, let us not use D, just a special case. Let us say some AZ, CZ, BZ and DZ with a new set of equations. Okay, this is your new set of equations. So now we will consider our case. Our case A is forgetting -1, -3, 0, -2. So there's a -1, -3, 0, -2. Okay. So what are its eigenvalues? Can anyone tell me?
One and sorry, -1 and -2.
Yes, it will be -1 and -2. Yes, Joshua. It will be -1 and -2. Yes, correct. And yes, Rahul method will be -1, -2. So you have got lambda is -1, -2. Good. Now we have to find the eigenvectors. So So can you find out and tell me what are the eigenvectors? Find out and let me know what are the eigenvectors for this. What is your V1 bar, V2 bar?
Sir, for lambda equal to -1, eigenvector I got is 1 minus 1 by 3.
Okay. You got 1 and minus 1 by 3. Okay. Joshi,
And
what did you get?
for
You got
lambda,
minus. Joshi has got 1 and minus 3. Joshi has got 1 and minus 3. Okay. Okay, for lambda is equal to minus 2, what did you get?
sorry, sir, 1 and minus 3, not 1 by 3.
Okay, you also got 1 and minus 3. Okay, good. So,
Then for second
yeah,
eigenvalue, lambda equal to -2,
Joshi has got 0, 1.
0,
What have you got?
0, 1, 0, 1, 0 and any value.
0 and any value. Okay, so 0 and 1. Okay, good. Both of them good. So you got V1 bar, V2 bar, you got. So, okay, so V1 bar is 1 minus 3, V2 bar is 0, 1. Okay, so what we will do is we'll consider the matrix M is equal to your V1 bar, V2 bar. We'll construct this matrix M in terms of V1 bar, V2 bar. So that will be what? Your 1 minus 3, 0 and 1. Okay, 1 minus 3 and 0 and 1. So now your AZ is what? M into A into M inverse. Okay, so your AZ is M into A into M inverse. So before you do this, can you tell me what will be M inverse? Can anyone tell me what is M inverse?
Uh, 1, 0, 3, 1.
1031 and
Determinant is one itself.
okay. Yeah. So for those who don't know, for a second order thing, if it is represented in ABCD, the M inverse would be BA minus B minus C upon AD minus BC. This is how you find the inverse of a second order matrix. It is very easy. So as Arun has told, we get it to be 1130. So M is what? M is 1 minus 301. A is, forget A time. A is minus 1, 0, minus 3, minus 2. So minus 1, 0, minus 3, minus 2. M inverse is 1031. So compute and tell me what is your AZ then in this case.
Sir, I don't know whether it is correct. Minus 1, 0,
Okay.
minus 6, minus 2.
Okay.
Yes, sir. Same.
Okay, same. How come?
We are not getting it as a diagonal matrix.
Yes, it should come as a diagonal matrix. Okay.
Minus
Ideally,
6 and minus 2.
no,
We
it should.
can factorize. Minus
You
1, 0, minus 3, and minus 1.
that you could, but actually AZ should come out to be what? Minus 1, 0, 0, and minus 2. This should be the desired form. So if this has happened, means we have made a mistake in the eigenvector. So let us go back and recheck our eigenvector.
Sir, I have a doubt in that equation.
Okay.
So, from what I remember from that previous course, is it M inverse same or M? I think it is M inverse A.
Sure. Because when we have derived over here, we have got,
Because usually we do is M x equal to M Z, but you have started with x equal to M inverse Z.
okay, that could be one thing. Z equal to mx, so x equal to m inverse z. Okay, that could be one reason. Maybe. Okay, so suppose we want to do that, then our, let us say our reason prime, that should be m inverse am, right? So that would be 1031 minus 10 minus 3 minus 2, 10 minus 3 1. Okay. Could you check what this comes out to be?
Yes, sir. Now it is getting -1, 0, 0, -2.
Okay, good. So, right. So what has happened is these things all are fine. These things all are fine. This is fine if I have used the conventions x equal to m inverse z. If I've used x equal to m inverse z, then this is fine. So you have to see the question what it says. But if I want to transform a coupled x to a decoupled z, then I will have I cannot use this m because it should be, let me say, this is your x coupled, your z decoupled, right? So what we have seen is we have used x equal to m inverse z. We have used x coupled is equal to m inverse z, right? Where this m inverse is actually so the derivations are fine, but if we want to do the similarity transformation to diagonalize, that is, if you want to do this diagonalization to find what to transform the coupled set of equations to a decoupled system, then this x coupled vector, you have to replace it with m into the z decoupled vector, where this m is the eigenvectors of the A matrix, the A coupled matrix. Okay. This is how you must do. We had gone in the opposite route. We had used m inverse z, which was we should have gone with the m into z method. That is the one which we must use for diagonalization. Any doubts in this? Or you want me to again clarify things? Okay, I'll proceed then. This is question 3. Let us consider Taylor series linearization. So we have this system here, and we have to find out its eigenvectors. Okay. So question 4, x1 dot x2 dot, this is equal to your x1 cube plus x2 minus 3, x1 cube plus x2 minus 3. This is 1 minus x1 x2, 1 minus x1 x2 minus x1 cos x2. Okay. So this actually is your x dot is equal to f of x, where x consists of the states x1 and x2. Okay. So first, is this a nonlinear system or a linear system?
Non-linear.
Okay, it is nonlinear, right? So it is nonlinear. So what are the equilibrium points of this system? How will we find the equilibrium points?
Put x dot equal to 0, and then we can solve those equations.
So first we have to find the equilibrium points. So as Aruna said, we have to substitute x dot is equal to 0. That implies x1 dot is equal to 0, x2 dot is equal to 0. So that means your x1 cube plus x2 minus 3 is equal to 0. and your 1 minus x1 x2 minus x1 cos x2 is equal to 0. Okay. So any idea how do we solve these equations? Any easy trick or hack?
Some iterative technique like Newton-Raphson.
This would require some iterative technique. Yeah.
Or if it's like 4 options are given, then we can plug in the options and see which one matches the answer.
Yeah, that would be a good way. That would be an easy one. No? So those are options are there. So I don't find a way to solve it currently over here. Okay. So let us hope in your exam, if such a question comes, you have been given your equilibrium point. Right? You have been given what is your x1 equilibrium, your x2 equilibrium, you have been given. Okay, assume it is given. Currently, I have not been able to give you that x1 equilibrium, x2 equilibrium. But that is okay. What we want is we want to find the linearized A matrix. We want to find your linearized A matrix. So to find a linearized A matrix, that we find out using what is known as a Jacobian matrix. And that comes using the concept of what is known as Taylor series. So your A is actually dou F by dou X. So that is actually equal to your dou F1, dou X1, dou F1, dou X2, dou F2, dou X1, dou F2, dou X2. Right? So this is your F1, this is your F2. Right? So what is dou F1 by dou X1? Dou F1 by dou X1?
2x1. Sorry, 3x x1 square.
Okay. What is dou F1 and by dou X2?
1.
Okay, 1. Okay. Dou F2 by dou X1?
Minus x2 minus cos x2.
Minus X2 minus cos X2. And then dou F2 by dou X2?
Minus x1 plus x1 sin x2.
Okay. Yeah, so when you differentiate cos, it becomes minus sign. That's correct. Okay, so this is your A matrix. And over here, you have to substitute your X1 is equal to X1 equilibrium, X2 is equal to X2 equilibrium. This is what you'll have to substitute. Then you will get a solution. Fine. Then you will get a matrix A. And then in the matrix, you'll have to you will get in some number format. And that number format, you will find the eigenvalues and you can find the eigenvector. Okay, that's the same way you can proceed with this question. So you want me to repeat this or should I proceed to the next question?
Clear, sir.
Okay. Let's go to the next question. Okay. This also is the same type. We'll skip this for now. Let us go for the phase portrait questions. Okay. So this is our question 6. That is f of x is equal to dx dt is equal to bx. Okay. So when you, I don't know which standard or which grade you learn, but there is something which we learn in maths, that is functions. Okay. So this is a function of x. This is a function of x. So we have our x, and this is f of x. Okay. This is equal to b into x. So that will be, it's like y equal to mx plus c kind of line. So since c is 0, intercept is 0, so it passes through the origin, right? So it is a line with the slope b. This is a line with the slope b. Okay. Till here, any query?
No, sir. B is positive, right?
B is the slope. So now, what do we have? If we solve this solution, that is this dx dt is equal to bx, we get x of t is equal to e raised to bt into x of 0, right? So, as b is positive, as your b is positive, this will, we will have not put the condition, your b should be greater than 0. Then what will happen if your b is greater than 0? Then your x of t will increase, will go to infinity. That means in this graph f of x, you don't have any time information. But what you could say is that it would rise, it would go on increasing. It would go on increasing. It may go from here to here in 1 second, from here to here in 1 second, here to here in 10 seconds. That could happen. So time information is not there. But what we can know in a general perspective is that x will go to infinity because my b is positive. Yeah. So like this question could come. This is like a first order case. They could ask you for a second order case also. It will be limited only till second order, first order, second order. So they could ask that, will it look like this? Will it look like this? Will it reduce? Or will it look like this? Will it increase like this? Or will it be like this? Will it be like this coming here? Will it be like this? They could ask such a question as well, right? So this is a case where it is unstable. This is the correct one. So these are the wrong options. Okay. Yeah. So I proceed to the next question.
Yes, sir.
Yeah. So this is your dynamical system. Okay. Yeah. So question 7, x1 dot x2 dot is equal to minus 2 0 0 minus 5 x1 x2. Okay. What do you want? We want the solution, phasor portrait, eigenvector, the first eigenvector. Okay. So we have x1 dot is equal to minus 2x1, x2 dot is equal to minus 5x2. So what will be your x1 of t and x2 of t?
E to the power minus 2t and e to the power minus 5t. Sorry, I forgot that. This one, initial condition.
So what will be the initial condition? Like your initial condition is x0, right? So should I
Yes.
put x0? But your x0 consists of your
Yes.
x1 0 and x2 0. So what should I put here?
x10.
Yes. It is x10.
Hmm.
And this is e raised to minus 5t x20.
That's right. Yes.
Okay. So what about others? Parvati, Joshi, Arun? Is this part clear or is there any confusion in this part?
No, sir.
Okay.
Clear.
Okay, great. So this is done. X1t, X2t you have got. So this is the solution. So is it stable or unstable? So what are the eigenvalues? First of all, what are the eigenvalues?
-2 and -5.
Okay, eigenvalues -2, -5. What type of point is it?
Stable.
So it is a stable node.
Stable
It's
node. Yeah.
a stable node because both are real. Hmm. Now, thank you, Joshi. So now, what we have to draw the phase portrait. So phase portrait is how x1 and x2 will look like. Hmm. So before drawing this, let me draw the time portrait. This is your time. This is also your time. This is the graph of x1. This is the graph of x2. Suppose this is your x1 of 0. Will decay like this. Suppose this is your x2 of 0. It will decay like this. Right? So x2 will decay faster because this is given by x2 0 e raised to minus 5t. But this is given by x1 0 e raised to minus 2t. So this will decay faster. So this will become very small, very fast. And this x1 will take some time, much more than compared to x2 to come very low, to go 10 to 0. So x1 decays slower, x2 decays faster. Okay. Now, let us say this is your x0, where this is your x10, and this is your x20. So we are starting from this point. This is the point we are at. We have seen, like you have found out what is the solution, how does the state decay. We have found that x1 decays slowly, x2 decays very fast. So how will it look? Will it go like this? Will it come like this? Will it go? Let me use a different color. Will it go like this? Like this, will it go? It should decay. It should go to 0. That's true, but how will it go? Or will it go like this? Which do you think is the correct option?
Second one, sir. That green one, because it decays faster, right? E to the -5t. So
Okay. Okay. So the green one is the correct option, right?
I think so. Yeah. Yeah.
Okay. What about others?
Yes, sir. Yes.
Because at this point, you will see that x2 has reduced more, x1 has reduced lesser. At this point, you will see x2 is quite less, but x1 is still quite a lot. Here again, you will see that x2 is much less, x1 is still quite a lot. Right? Because x2 is in this much, but x1 is in this much in terms of this much. Right? That's why this green curve is the correct one. Hmm. Right?
Yes, sir. If they by chance interchange the axis, then it will be blue, right? Like if they
Yes,
make
yes,
that
yes.
as
Correct, correct, correct. Yeah. If we interchange the axis or we use a different matrix, it would be the opposite one. Yeah. Hmm. Okay. Now, all right. So, Rishi, I'll just repeat it once more. So this is your x1. It is given by x1 0 e raised to minus 2t. So if you will draw a line, this is the same time t. So if you will see, this has fallen this much, but this has fallen just little. Okay. Now let us draw it again over here. Right? Here, this has fallen so much, while this has fallen less. Right? So if we will see this curve, let us say this is our initial condition x0. Where this is my x1 0, this is my x2 0. Since my x2 is decaying quite fast, there could be three options. It could either go in a straight line, it could decay in the green pattern, or it could decay in the blue pattern. All right. So now, if we'll see the green pattern, which we have decided is the correct one, let us say at this point over here, this is a point at some time, at some instant of time. In that time, we will see that our x2 has fallen from this point to this point. That is, x2 has fallen so much. But what is fallen of my x1? X1 is just fallen so less. Then I will go to this point over here. There I will check my x2 has fallen so much. But my x1 has fallen a little less. It's quite less as compared to x2. And when we will see the response in time, you will observe that x2 will fall much faster and much more as compared to x1. So from that, we can conclude that the green one, this is the correct option. Sorry, this is the correct option. Okay. 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 So now, what are we supposed to do? We have to find the eigenvector of the slower eigenvalue. So which is the slower eigenvalue? -2 is the slower eigenvalue, or -5 is the slower?
-2.
Okay. So good.
-2 is the slower. Yeah.
Yes. So -2 is the slower eigenvalue. Right? So you have to find the eigenvector corresponding to -2. So I trust you can do that. You can do that. Okay, so let us just do some MATLAB demonstration. Just for you. So the code. So what was our A11? It is -2. A12 is 0, A21 is 0, A22 is -5. Okay, -5. Initial condition, let us take it as 1, 1. Okay. Let us take it as 1 second or 10 seconds. Where 1, we do subplot, it will be better. 3, 1, 2, 1 row, 1 column. Let us check how it goes. Yeah. So let me run this section. So let me run this section and run the next section. Okay. Right. This this is wrong. 1 minute. This explain button is on. So I will configure to then I go in. Yeah. So we You don't. So you don't here also. Let me run this section again. So if you see this curve, this my x2 is decaying very fast, x1 is decaying slower. Okay, x1 is decaying slower. So let me plot it for less time, for 2 seconds. Let us see. Let us run it. Okay. So it's like this, right? So x1 is following one. X1 is falling quite fast, x2 is falling, means x1 is falling slowly, x2 is falling quite fast. Now, let us see the phase portrait. See the phase portrait, that is this. Phase portrait is what? Where we are plotting x1 versus x2. Where your x label is your x1 and your y label is your x2. Okay. We'll run this section. This is the way it looks. And as you guys have told correctly, this is the way the phase portrait will look like. So probably you would have known there's something known as XY mode in the oscilloscope. Probably you might have checked. And maybe you might have studied earlier some Lissajous patterns. All those things are there, right? So this is like one way of looking at it. Like this is the phase portrait. How X1 looks in comparison with X2. To make it better, let us try green color. Okay, to maintain consistency, this is the green color which we used in our thing. So this is how X1 and X2 look like, right? So this is the correct phase portrait. Now, Sir shown, sorry, Sir had shown something known as your vector field. Let us see this vector field. Okay. So this is your vector field. What does your vector field say? That if you're starting from this point over here, you would go in this direction, in this direction. If you start from here, you will go in this direction. So you'll be going like this. Now after some time, the vector field will be like this. It will go on like that. Okay. So this will show that you're going to come in this direction. Right. Let me uh, make the number of points more. 15. Look like this. Like small vectors are there, different points. So they are showing that it will follow this pattern. It will follow like this pattern, it will follow. Okay. Right. Let us see one more thing. How can I plot these plots as well? Someone not showing the thing. I'll have to check. Because I wanted to plot your actual trajectory on this vector field. I have to check that code to see. Okay. So this part I'll look into it. So till then, let me show something else. So we consider case where your eigenvector was -2 and one is -5. Let us interchange it. Let us make this -5 and this -2. If you will see that, then when you will see, it looks like this, right? Here this will decay faster, this will decay slower, and then this curve will be in this state. It will look like this, right? Now, let us consider case when both are equal. This is -5, this also is -5. So if we run it, it will look like a straight line. There's a straight line going from top to bottom. Okay. So any queries till this part?
No, sir.
Okay. Let us consider a case where this is 10, this is 10. When you run it, this, yeah, again, the values becoming, we have to check the eigenvalue of A. So check the eigenvalue of A. This -6, -4, okay. Eigenvalue of A is -6, -4, so it is closely almost a straight line. And this is how your x1 and x2 is looking. So x1 is decaying much faster. No, x1 is decaying slower, x2 is decaying much faster. It's almost similar. So I told about the stable node, stable focus and unstable focus. So does anyone remember about that? Or you guys have not yet gone through the lectures? Okay,
Not
Not
finished that last
completely.
one.
No.
Yeah.
okay. Yeah.
Sir,
Yeah.
one,
Mhm.
sir, can you show that last plot, that QR plot for different cases? We studied 5 cases. So lambda, positive, negative.
Yeah, that's what I was trying to figure out. Let me show for the case when lambda is positive. Yeah, lambda is
I
positive.
think if we can make it diagonal,
Yes, I made it diagonal. One is negative, one is positive. Let us see. Let us run it. Okay. So x1 goes down, x2 goes infinity, and your pivot plot looks like this. I think it's better if I reduce the resolution of the pivot plot. It will make more sense then. Looks like this. Okay. So in x1 direction, it is going to 0. X1, when it's in the x1 axis, it will go to 0. But when it's in the x2 axis, the y-axis, it will go to infinity, it will go to infinity. So any point over here, suppose there's a point over here, it would want to go, x1 will say you go in this direction. X2 will take it up. Then again over here, it will go in this direction, x2 will take it up. This direction, take it up. So like that, it will go off to infinity. But unless, if at all, it is by lucky chance, it is within this x1 axis, then it will go on like this, like this, like this to your origin. Like that. Okay. So this is a saddle point, right?
Sir, here eigenvalue corresponding to x1 is negative and the other one is positive. Is it like that?
If you see, yes. Corresponding to x1 is negative, corresponding to x2 is positive. Okay. Let us consider case both are positive. Both are positive. So these are unstable node. So here it will go out, here also will go out, here also will go out, here also will go out. Anywhere in between, he'll go out. He'll go out, out. It will all go out. This is says it is a completely unstable point. So your 0, 0 is your unstable point. Okay. Let's check the case where I want to get the stable focus case. I'm not able to get it. Let us try once. Let me try once. Simplify. So be minus 1. Let's check. Right. So let me run for more time. It should run for more time. Let me run for more time. Next time, 20 seconds I will get it. We run it again. Is it unstable or stable? Oh, it's unstable. Let me make it stable, please. Stable, please. Okay. So it has an oscillatory behavior. It is going below 0. In your previous cases, because it had exponential behavior, it did not go below 0. It was decaying to 0 at around infinity. But here, because it has that complex conjugate, that is why it has this oscillatory behavior. And this oscillatory behavior, you will see in your phase portrait. Here, from this point, it is going below 0 and coming here. So this is that oscillatory portion you are seeing. Okay. And how do we check it?
Sir, I cannot see your screen. I don't know whether is there any network issue in my side.
No, same. Even I think your screenshot sharing, sir.
Oh. Okay. Sorry. Okay. Sorry. Okay. Here. So let me say my A matrix. A matrix is given in this form. And if I see the eigenvalues of this A matrix, you will get it is -5 plus 5j, -5 minus 5j. Okay, so they are complex conjugates. So if you will draw how they look, how the response looks like, you will see like this. Okay. Your x1 is going below 0. Your x2 also is going below 0. But in the previous exponential case, x1 did not go below 0. It went to 0 almost at infinity. It didn't cross 0. Similarly, your x2 also didn't cross 0. But here they are crossing. In the case when they are complex conjugates. And your phase portrait also you will look like this. It is going from here, it is going below 0 and coming here. This is because they are complex conjugates, so it is a stable focus because it is decaying to 0. Okay. So you're able to see this case? So if you notice over here,
Yes, sir.
there is oscillatory behavior in x1 There's oscillatory behavior in X2 as well. And see, it is decaying like this. It is going like this. So this is known as a stable focus. Okay. And why this has happened is, you will see the eigenvalues of A. They are negative real part, but they are complex conjugates. That's why you have this oscillatory behavior. So any queries about this?
If they are positive real part, complex conjugate with
Yes,
positive real part,
I'll
then
see
it
that.
will go spiral outward. Is it
Yes,
like
let's
that?
see that. Let's see that. See, it is spiraling outwards. It's going out. So this is your unstable focus.
Okay, sir.
Like that over here, finally it goes unbounded. It's unstable. Yeah. Okay. So any other queries or doubts?
No, sir. Thank you.
Okay. Okay then. Thank you. I'll end the meeting. Good night.